This lecture will discuss music and standing waves. Sound is a longitudinal wave that requires a medium to travel through. The speed of sound varies with temperature. It is 343 meters per second at 20 degrees. The pitch of a sound is referring to its frequency. The higher the pitch, the higher the frequency. A standing wave is fixed in location, but oscillates with time. These waves are found on strings with both ends fixed, such as in a musical instrument, and also in vibrating columns of air. Antinodes refer to the area of highest amplitude, and nodes refer to the points between the antinodes that have no movement. On a vibrating string, nodes always form at the end where the string is held or tied down. There must be an integral number of half wavelengths on the string. This means that only certain frequencies are possible. Points on the string which never move are called nodes. Those which have the maximum movement are called antinodes. The fundamental or lowest frequency on a fixed string has a wavelength twice the length of the string. Higher frequencies are called harmonics. The lowest harmonic, F1, is equal to the velocity of the wave divided by 2 times the length of the string, L. The wavelength of the fundamental frequency, lambda 1, is equal to 2 times the length of the string, L. The frequency and the wavelength of the nth harmonic, with n equal to 1, 2, 3, so on, is given by the general equation shown on the slide. A guitar string of length 2m vibrates at its fundamental frequency. Find the first 3 harmonic frequencies it will vibrate at if the speed of the wave is 20 meters per second. Substituting into the formula for frequency, we get F1 equals NV over 2L equals 1 times 20 meters per second divided by 2 times 2 meters equals 5 hertz. F2 would be 2 times 20 meters per second divided by 2 times 2 meters, or 10 hertz. F3 would be 3 times 20 meters per second divided by 2 times 2 meters, which is 30 hertz. Notice that Fn is equal to n times the F1. In order for different strings to have different fundamental frequencies, they must differ in length and or linear density. A guitar string that are all the same length, but the density varies. In a piano, the strings vary in both length and density. This gives the sound box of a grand piano its characteristic shape. One of the length and material of the string is decided. Individual strings may be tuned to the exact desired frequencies by changing the tension. Musical instruments are usually designed so that the variation in tension between the different strings is small. This helps prevent warping and other damage. Standing waves can also be excited in columns of air, such as soda bottles, woodwind instruments, or organ pipes. As indicated in the drawing, when a pipe is closed only on one end is a node, N, and the other open end is an antinode, A. In this case, the fundamental wavelength is 4 times the length of the pipe, and only odd-numbered harmonics appear. Looking at the diagrams, we see that even numbered harmonics cannot open or happen in open-ended pipes. The frequency equals N times V over 4L. Note that N is 1, 3, 5, 7, and so on in this case. A student blows over a Coke bottle. The air column in the bottle is 20 centimeters tall. What are the first 3 harmonic frequencies that can vibrate? The speed of the wave is the speed of sound. Plugging in, F1 equals NB over 4L, which gives us 429 hertz. The next harmonic is N equals 3, so 3 times F1 is 1287 hertz, and the third harmonic is 5 times F1, or 2145 hertz. If the tube is open at both ends are antinodes, and the sequence of harmonics is the same as that on a string. The math is the same as for a string. So the fundamental frequency is found using the same equation as that for a standing wave on the string, and the harmonics vary with n equals 1, 2, 3, and so on. Beats are an interference pattern in time rather than in space. If two sounds are very close in frequency, their sum also has a periodic time dependence, although with a much lower frequency. The new sound will have a definite wah-wah sound. The wah is an area of louder constructive pitch, and the silence in between them is due to destructive interference. When instruments are tuned, the whole object is to get rid of the beat frequency. If the beat frequency is 2 Hz, then you hear 2 wahs every second. So the lower the beat frequency, the closer the pitch of the two notes. The beat frequency is simple to calculate. Just take the difference between the two frequencies. So the beat frequencies for two sounds of 200 Hz and 225 Hz will be 25 Hz. This is not a very pleasant sound. The higher the beat frequency, the uglier it sounds.